Now we are ready to run a simulation. So how do we do that? Well, we gotta go to the terminal once again. So one way to do this in a Mac is just to right click on a file that is in the folder that we want to, to right click on a folder that you want to open, say new terminal at folder, and directly it will open a terminal there. Otherwise, you can navigate and you can check online some instructions on how to use the terminal. So once you are in here, you see that we are in the folder called example. It is indeed where we want to be. If we type ls on a Mac or a Linux, it gives you the content, DETO2D, input2D. This is exactly what we have in the folder. If you're on Windows, you do this by typing dir. And now we want to run the code. How do we run the code? It's very simple. ./DETO2D. So this is the name of the executable, and then the name of the input file, input.dat, and then you press enter. Notice that if you are in Windows, instead of /, you should use // So this slash here, //deto is the command in Windows. But on Mac or Unix, Linux is this one. So you press enter, and if the code is running, it should start giving you screen output like this and produce a bunch of files, which are the files that the code is progressively populating as its own output. So let's start from the screen output here. There's something that is preliminary preparation, done, so it's getting to the point of running the optimization. Step 1 is the step that starts with the same she that you gave as a she init in the input file, and then it's doing the minimization. So these steps here, these 10,000, 20,000, 30,000 are the steps of optimization. So it is the code that is progressively trying to impose the displacement and let the system sit under the imposed displacement. Then there is a bunch of things being plotted here. You don't have to worry about them. The only thing that you may worry about sometimes is this first column here, which is the same as this one, that is giving you the energy in the system, the strain energy. So the more you are straining the system, the more displacement you are imposing, the more you expect this number to increase, and indeed it is increasing. It is taking, the first number is how many steps the simulation has run, the simulator has run for, the minimization, the energy minimization that gives you the static equilibrium has run for, and it is giving you 10,000, 20,000, 30,000. Why is it giving you in unit of 10,000? Well, because if you remember your input script, when you set the quick min, you told it to give you output every 10,000 steps. So it is giving you output every 10,000 steps. And then it goes up to 100,000. What happens at 100,000? Well, if you go back again to the input script, you are imposing displacement at a rate of 2 10 to the minus 4 every step is 0.02 seconds. So you're actually imposing 4 times 10 to the minus 6 millimeters of displacement at each step of the minimizer. But we want to get eventually, so 4 10 to the minus 6, remember, we want to get to 4 10 to the minus 1. That's the displacement we want to impose. So if the code is reaching equilibrium as soon as it hits the imposed displacement, then it will take 100,000 steps, 10 to the power 5. And this is indeed what is happening here. It's taking 10 to the power 5 steps to reach equilibrium under the imposed displacement. So to impose a displacement of 0.4 millimeters, and then the system is already at equilibrium when it gets there. This means that we are applying the displacement sufficiently slowly. And then this is the first solution. This is the energy, the strain energy in the system at this imposed displacement for the initial distribution of xi, where xi is the same, equal to 0.3 everywhere according to our input file. Then the optimizer does a sensitivity analysis, updates the distribution of x's, and then starts again imposing the displacement from the undeformed configuration. So a couple of things you can note. One thing that you can notice here is that again the energy is increasing while you are increasing the imposed displacement from 0 to 0.4, but this time the final value is higher than before. Why is that? Well, because the system is becoming stiffer, we are redistributing the mass to make the system stiffer. As a consequence, it takes more energy to deform it to the desired imposed displacement. So it's a good news that for this kind of optimization, which is impose displacement, energy maximization. In step 2 of the optimization, the final energy is greater than at the end of step 1. It means that we are redistributing the Xi in such a way that it's making the system indeed stiffer. And then we move to step 3, similar story, but what we see here is that actually the system doesn't stop at 100,000. So why is it happening? So the energy is greater, but this time it increases up to 100,000 and then it decreases up to 130,000. So what is happening here? Well, what is happening here is nothing but what we saw in a previous video, and it's shown here. In the first 2 steps, we were going slow enough to hit the imposed displacement and the system was already at equilibrium. In this third case, when the structure is stiffer, the fact that we are going to that rate is actually overshooting a little bit. So it takes a few additional steps, namely about 30,000 additional steps of the minimizer to bring the system back to this equilibrium point. But in doing this, when you get to the top, you get a high energy, and when you are progressively decreasing the force by further relaxing the system, the strain energy is decreasing. And indeed, when you hit 100,000, all the imposed displacement has been placed, and the rest is relaxation, is minimization of energy, so it is reducing the strain energy. And a similar story happens at 100 at step 4. Again, it goes from 3 × 10⁻⁻1 to 5 × 10⁻⁻1, so the system is stiffer, and again there is a little bit of overshoot, a bit less than before, just 10,000 steps extra. Step 5, actually there is no overshoot anymore, and the strain energy at the end continues to increase. So we are making indeed our system stiffer and stiffer, as we showed a few videos ago. This is what is happening. Every time we are going through a steeper curve to a higher value of energy under the curve itself. So this is all what you need to know about the screen input, output. It keeps on going here, let's let it go. But actually, for the purpose of this example, we can stop the simulation here, don't let it go too far. And to stop a simulation on a Unix system, you have to press Ctrl+C. I think so you have to click on the terminal and press Ctrl+C, and this breaks the simulation. I believe it is the same command on Windows, but in case it is not, well, do a Google search to see how you can stop a running simulation on a terminal. On a Unix system, it is Ctrl+C. So you click on the terminal, you keep Ctrl pressed, and you press the letter C. So besides the screen output, what else is the code producing? Well, let's start with the DETO and the thermo.txt. As we said, the DETO is the one that you can load into this program called Ovito, and we will see later how it works. And when you learn how to load it correctly, then it will give you, the only thing that the DETO gives you is the first step, it gives you the equilibrium position for the structure with the initial uniform Xi that you have given it, and then it keeps the final equilibrium position and gives you the new distributions of X's. So essentially, it's a collection of how the structure looks like in terms of deformation and distribution of X's at every final step of this optimization. So it's taking the structure at this initial step here, step 0 actually, that is not shown here, then at step 100,000 for the first minimization, and then this one here, at the end of each optimization steps, it's giving you the deformed shape and the distribution of X's. Corresponding to this file, at each snapshot that you get in this DETO you also get a line in this thermo.txt file. And this thermo.txt file looks like this. The first column is the optimization step. So 0 is before you're starting optimization. Step 1 is at the end of this DETO step 1 here, which corresponds to the second snapshot in that DETO file that we showed before, DETO. And then step 2, 3, 4, so for each DETO step that is completed, you see we went up to 12 and then at 13 we stopped it. So for each DETO step, we get what? She total. She total is the sum of the she's of all the particles in the system. You remember that in our exercise we wanted 0.3 times, we wanted the volume fraction eventually, the F, so the fraction of particles with mass equal to 1 to be 0.3 of the total, meaning that the total she should be equal to 0.3 times the number of particles in the simulation. Specifically in this exercise, the number of particles in the simulation is 908, so if you do times 0.3, you get indeed that this is 272.7, which is exactly or very close to what the code is fixing at the end of each optimization step. So you start with it because you impose 0.3 to all the particles, and then as the code progresses, it's redistributing the she, but still if you sum the she's of all the particles, some will have 0, some will have 1, some will be in between. If you take the sum of all of them, should always be n times the target f that you gave in the input file. So this target f here. Okay? And indeed, it is in this example. It's always around 272.7. Then there is C. C is the strain energy in the system, is the quantity that in this case we're trying to maximize via the optimization process, and indeed you see that it's increasing. 0 initially because the initial snapshot is thus the undeformed structure, then it is low because this is the case where the mass, the she is distributed uniformly in all the structure being 0.3, but as you concentrate in the most strategical places the she, this is increasing up to 3.95 in this case. And then what do we have? Then we have the quantities that we asked our input file to add to the thermal. So you see that in the input file we said at the very end, add to the thermal the y position of particle 888. Well, the y position of particle 888 is this column here. So at the very beginning of the simulation where there is no deformation applied, it is 57.1576, and in all the other cases, at the end of every step, it is this value minus 0.4 millimeters. So 0.15 minus 0.4 is 0.7. Okay? And in all the cases it's the same because we are always imposing the same displacement. It would be different if you were imposing a force instead. As the structure becomes stiffer, the final displacement should progressively reduce, and so this value should be closer and closer to the initial one. But in this case here we are imposing the displacement, so of course the value of the final y is always the initial one minus 0.4 at the end of every minimization in every optimization step. And then what do we have? All the forces that we added here. Vertical force Fy for particle 885 is this value here, then 886, 7, 8, 9, 90, 91, 92. And then in this case, because the structure is becoming stiffer, you can expect this value of the forces on each of the top particle to which we are imposing the displacement. We expect that we have to apply a greater and greater force as the structure is progressively getting stiffer. And indeed, the values of all these forces, you see that they increase during this optimization process. So something that we can do with this file is to plot the values in Excel and extract some nice graphs, and we will do this in a later video. Let's continue our overview of the outputs. We looked at all dump, DETO2D, thermo.txt. What is thermo-all? Thermo-all is exactly the same thing as thermo.txt, exactly the same structure, so exactly the same columns, step, total she, C value, which is the strain energy, total strain energy in the system, the one we are maximizing, vertical position of particle 888, and then the forces on all the particles at the top center. But in this case, there is one snapshot recorded for each output on the screen and for each output in the all dump file. So this means that every time that we are monitoring the progressively increasing deflection of the beam, we are also plotting all the quantities that we asked to record in the thermal. Why is this useful? Well, because if you want to write a force displacement curve at a generic step of the optimization. So if you actually want to draw curves like these, it is not enough to take the initial and the final value. Well, it is in this case because it's a linear interaction, linear system. But if you were using non-linear interactions, for example, you wouldn't be able to reconstruct the force displacement curve only from the thermal that gives you the initial and final value of the forces only. However, from the thermal all, every 10,000 incremental steps of displacement, it gives you the corresponding values of the displacement itself, y, so the position of the central particle, and also of all the forces in the top layer. And if you take the sum of all the forces here, so the sum of these forces I, for these 8 particles in the center, is the total force that you can plot against every corresponding displacement every 10,000 steps. So you can use this information here to generate force displacement curves like the ones that I'm showing here. And so you can see how indeed this force displacement curve is becoming steeper and steeper as the optimization progresses. So how do you know when one optimization step starts and finishes in this file here? Well, simple. Here we start from the undeformed configuration. Then we start applying the displacement and we go to step 10,001. So it does it one step later, this one. So more or less the same as when the DETO is printed one step later. Then you keep going, you see that it's progressively increasing the C, so we are adding strain to the system. The displacement here is increasing because the Y position of the central particle is decreasing. So here we are increasing the applied displacement. You see 56.9, 56.95, 56.91, 87, 83, 79, 57. So here we are at the initial minus 0.4, and then here what is happening is that the displacement goes back to the top, goes back to the initial value, and the forces go back to 0. So this is a clear indication when the forces go back to 0 and the displacement you're monitoring goes back to the initial one. This is a clear indication that one optimization step is over and the next one is starting. And indeed, we know that it took 100,000 steps to run the first optimization step, so this one lasted 100,000 steps. Indeed, after 100,000 steps, you have finished the first iteration, the first minimization, and you can update now the sheaves. So in doing this, you have data to construct point by point this initial total force versus imposed displacement curve with a progressively increasing displacement and progressively increasing sum of the forces. We will do in a later video this using Excel. And then you can repeat the same for the second optimization step, starting from 0 forces to the maximum, and then the third step will start 0 with the 0 forces and going down to the maximum, etc. So for each step of the optimization, you can draw a force displacement curve from the data that you asked your code to save into the thermal all file. The data that you are saving in the thermal all file are exactly the same that you save in the thermal. They are given by you as add thermal properties in the input file. The only difference is that they are done during the minimization process that finds the static equilibrium within each optimization step, whereas the thermo.txt only gives you the final value at the end of the optimization step for the energy and for whatever quantity you are asking to add to the thermal.